Okay, so today is we'll be going over how to solve the XOR problem with quantum machine learning. So the XOR problem is not that common these days, but it used to be a sort of canonical example in machine learning because it was shown that single layer perceptron models cannot solve it because it's not linearly separable. And so the XOR problem basically is just solving for input 1 XOR input 2, and that is labeled with either 0 or 1. And so it's pretty easy to construct a table of what that looks like. And we can see that this is not linearly separable because it would be 0, 1, 1, 0 if we were to graph something like this. And so from there stemmed a lot of important research in the area of multi-layer perceptrons. But it's pretty simple to solve with when you have multiple neurons or multiple perceptrons. So this is basically just what we're going to be going over today using TensorFlow-Quantum. And so in this case, this is an extension. Last time we talked about using TensorFlow-Quantum with quantum data, or naturally quantum data, I should say. This time we're working with classical data because the input is just a binary number or two binary numbers. This is not an unparametrized quantum circuit and therefore needs to be converted into quantum circuit. And so we'll be discussing how to do that today. And so as before, we want to first make data, make the model, fit the model, and then analyze it. And we're applying the same step-based process to this technique. And within this, there'll be a couple new things. Specifically within data, we'll talk about classical to quantum conversions. In the model, we'll talk about pooling operations, purely quantum pooling, I should note. And in fitting, we'll talk about importance of the learning rate. And so there's a lot of new, even though this is probably a simpler or just a simple problem as yesterday, there's a lot of new sort of ideas here and importance for quantum machine learning. So let's just jump right into the code. Let me just zoom in and pop this up. Same imports as before. So if we scroll down, we can see, once again, we're creating the data here. And then we are applying the same readout operators concept as yesterday. This time we use the Z readout operator just to work in the computational basis, which is what the Z basis is called. Same inputs, string, because this is, in order to work with a quantum circuit, you have to input of data type string, and same, it's a classification 0 or 1, so we use the same hinge functionality. But first, let's talk about converting classical to quantum data. So if we go to the make data function, we can see I just hard-coded it here because there's 4 possible cases. And so exactly how do we convert classical data to quantum data? That in itself is a substantial research area. There's a lot of different techniques, because what I'm going to show here does not actually utilize the optimal sort of encoding technique, which would be So for this classical conversion, as I said, it's not optimal because you could optimally encode classical data in log n qubits, log base 2, because you know, there's the potential for n qubits to represent 2 to the n values as their amplitude, and that's the so-called amplitude encoding. But that's a lot more, usually a lot more complex to encode, and can often be challenging because it usually requires a very large number of gates or a very large number of qubits to encode. And so it may not always be the best technique for this machine learning approach. And so in this case, we're just using basically computational basis encoding, which takes the binary and just for each qubit, just flips it. Basically, you just apply the X gate or the quantum NOT gate to the qubit that is a 1, and if you leave the zeros as they are, I just put the identity matrix or the identity gate, which does nothing. It has no impact on the state of the qubit. It's just there to ensure that there is something in that place. It's just a aspect of circ and TensorFlow-Quantum. And so as we can see, for 0 and 0, they're both identity gates, and -1 just for the hinge loss. For 1 and 0, you apply the X gate to the first qubit. For 0 and 1, you apply the X gate to the second qubit. And for 1 and 1, you apply it to both of them. And in this case, the testing and training is the same. These are only 4 possible combinations of XOR. So now we can, now that we have data, the testing and training is actually the same. It doesn't really matter to separate them that much in this case. We can actually make the circuit. And so this operation is a little more complex this time, even though this layer is literally identical. I just copied it over from the previous code. The make circuit is usually where a lot of the differences come in. And so in this case, we can see it's a lot more complicated. And so there's 2 qubits. And so we apply the Rx, Ry, Rz to each of them. And you can do this in different ways too, because you can decompose unitary gates, an arbitrary unitary rotation, into just, X's and Z's. So, you could say the Y isn't necessary. I just have one of each here just for completeness. And so we have all of these weights. Then we'll have weights for a pooling layer, which I'll get into in a second, and then we have the circuit. So right off the bat, we'll notice that it's different, and that is because we apply a C0 to the qubits. So the C0 gate, just as a quick reminder, is the gate often represented, if you have 2 qubits going along here, it's represented often looking something like this. It's also called the controlled NOT gate because that's what it is. And so it converts, if we consider some sort of truth table for the pure states, the potential pure states, we can see that these are unchanged when the controlling, here this first qubit is the controlling qubit, so maybe we can do that, but in the cases where the controlling qubit is 1, it flips the second qubit. It's a little more complex when they're not, well, it's the same operation when they're not pure states, but the impact is different. And so, but in this case, they all are pure states. So you might think, well, why do this? It results, it flips these two, but it doesn't have any other impact on the actual system, right? And that's where another important aspect of quantum machine learning comes in, and quantum computing really, which is entanglement. So all of these states are entangled. And so when these two states are entangled, that means they're no longer separable in terms of wave functions. So you can't do, if this was the wave function of qubit 0 and this was the wave function of qubit 1, this doesn't work. You only have, this is, when they're entangled, you can't have this property. And so, well, in some cases it may be true, but that's sort of an explanation, like it's not always true. And so we do this because when states are entangled, we can see that changes on either one of these will, in some sense, impact both of them. That's kind of maybe a poor choice of words because they're not really separate anymore. There's one, combined wave function going forward. And so we entangle them to enable sort of operations between them that can affect the whole of the wave function. So I kind of like to think of this as, if you have the normal, neural network here with your input nodes, they're then densely, maybe we have they're then densely connected to the output nodes. That's pretty messy, but you can see in a dense network every neuron is connected to every other neuron, but this couldn't really be possible if you had some sort of qubit here. It's going to this one. It can't also go to another qubit because of the no cloning theorem. So we can't really do the exact replication, but this sort of operation, I like to think of, it's not, necessarily mathematically the same thing, but in terms of the ability for this single, neuron or qubit to impact all of the states, is similar to the concept of entanglement, in which the single operation impacts the whole state because the whole state is entangled in this one wave function. So that's the importance of entanglement, and you'll often see, let me go back to the code, you'll often see entanglement in these quantum layers. And so there's also different types of entanglement. You can have strongly entangled. In this case, it is because there's only 2 qubits, and that's where, you can apply CNOT gates to every single one of the qubits or not. And so in this case, this is just, sort of a standard practice. And so then we apply the Rx, Ry, Rz to each qubit. And that's pretty straightforward, same as last time. And then we applied a 2 qubit pooling operation. And this is directly from, this implementation comes from TensorFlow-Quantum and is from the QCNN paper, which is, I forget the authors right now, but I'll put it in the description. Quantum Convolutional Networks came out in 2018. It's an interesting paper, and they introduced this idea of a quantum pooling operation, which we use here. And so in this case, the quantum pooling operation takes 2 qubits and reduces it to 1, similar to what a classical pooling operation is, where you're sort of reducing the dimensionality. And so in this case, what they do is they apply 1 qubit unitaries to each of the qubits, which you can see being done here. And this is just how they define the 1 qubit unitary. And then they apply a CNOT gate to disentangle the states. Because, as we said before, any quantum gate is a unitary gate or a unitary matrix, and so it can be undone. And so we disentangle the states, and then we do the inverse of the operations on this sync basis. So you can sort of see we're not like copying states or anything. There's the idea of transferring or reducing this information. And so an important difference between this and the classical point operation is the quantum point operation is a parametrized operation. As you can see here, these symbols are referenced and are defined here. And so this is, a substantial difference. Normally with, like max point operations, you just take the max of every column or however you define it, or average point or something like that. In this case, it is, however, parametrized. And an important note, you might notice I do this all by hand, which is kind of unnecessary. I just want to show it for clarity, but we can see here how you can generate an arbitrary number of symbols by just using this colon operation. And so now with the 2-qubit pooling, we pool the qubit 0, the top qubit, into the second one. And so our readout operator is just applied to the second one, because that's the one that's we pooled into. So then we define the circuit exactly the same as last time. I literally just copied this part over. And all of this is pretty much the same with a couple exceptions. So first of all, the learning rate is pretty high here, and we'll discuss that in a second. We can see the epochs are larger, and the reason for this is because I'm actually here doing true gradient descent. A lot of times, and last time we did mini batch gradient descent. In this case, we're doing over the entire data set, and then doing gradient descent, which is true gradient descent. We could change this to 1 for stochastic gradient descent, but we'll leave it at 4 for now. And I'll show first the results. I have already run this code because it's 512 epochs, so I didn't want to force anyone to sit through that. So we can see that the code has already been run here. You can see that accuracy is 1, the loss is 0. So what I'm going to do now is show these graphs of same graphs as before, the loss and accuracy. Training and validation don't really matter as much because they're the same, values. So we can see the training loss here. You can see it decreases over time until about epoch 300 when it hits 0, and I just keep going. So then we'll see the accuracy, and this graph is not quite as pretty, perhaps, but we can see that there are very jagged lines because the accuracy only has a few possible combinations. You can't have, more than, you just have this sort of 75% accurate, 100%, and 50%. And the reason it, doesn't go any lower, you might be thinking, oh, you could misjudge all of them, and that's possible. But if you're just picking randomly, or you pick all 1s or all 0s, in this case all 0s because it is, remember, 0 initialized, then you're just going to get half of them right because you're just guessing half of them. And so this isn't as an exciting graph, but I will save it nonetheless. And so we can see that you can solve the XOR problem with quantum variational circuits using TensorFlow-Quantum. So before we finish up, I just want to show one thing. If we change the batch size to 1, we can reduce the epochs. I'm going to leave the learning rate the same. And now if I run this, this will be a lot quicker. Let me make sure I saved it. Yep. We can see that it takes a second to generate, but we can see that in this case, the stochastic gradient descent works just as well, and in fact better, because it takes less time than the true gradient descent. And so also we can see here what the circuit actually looks like, and I'll get to that when this is done training. You can see the accuracy is now 100, and we can see the loss is hitting 0. So I'll show the graphs in just a sec. But first, I want to scroll up, and you can see the circuit here. So we can see the C0 gate. And now we see the rotation X, rotation Y, rotation Z as pretty similar to before. Now this part, this whole section, very long, is the pooling layer. So we can see it applies the unitary to both of them. And then it applies C0 to disentangle them, and it then applies the inverse of this operation. You can see the negative Z, negative Y, negative X. So that's the pooling operation diagram. Now I can show the same graphs as before. And now we can see the training loss. We can see it reaches the same loss in a much smaller amount of time. And then we can see the training accuracy, which is pretty much the same thing. And it'll be pretty comparable, 100% accuracy in a similarly small amount of time. And now the last thing I want to do is show that the learning rate here, you'll see this in a fair amount of quantum machine learning code, can be very high. Normally you might set the learning rate to be something, decreasing over time, maybe in something like reinforcement learning, but you might set it to be, 1 times 10 to the negative third, 1 times 10 to the negative fourth, something like that, maybe decreasing. You might have some schedule for that, but here you'll see this a lot actually, or a fair more than you would see in classical machine learning. Pretty surprisingly high learning rate. So if we set the learning rate to 0.1, which is probably higher than anything you would ever do in classical machine learning, then we just run this code real quick. You can see I decreased the number of epochs again to 64 because this learning rate increase helps accelerate the process, and hopefully we'll see this pretty quickly. And this will be the last thing. Once again, I'll post all this code, so I encourage you to look at it, check it out. Yeah, you can see already it's hit 100% accuracy. The loss isn't quite 0, but it's getting pretty close. So let me show this. We could see the loss drastically decreasing. And if we show accuracy, we can see it almost immediately goes to the correct accuracy. And so, yep, there we go. There's multiple ways to solve the XOR problem in quantum machine learning, or I should say using quantum machine learning with classical data. And so once again, the key takeaways here are, if I go back to this drawing screen, we can see that we have to, when working with classical data, we have to do classical to quantum. We have to convert that somehow. In this case, we did computational basis encoding, which just is basically binary, fancy word for binary encoding. Now this is difficult if you have, suppose you wanted to do something like the image data set of numbers. I think this is correct spelling. This is hard to convert because if you have binary, converting floating point values to binary or something like that would be huge. So it would require a huge number of qubits. So you can't really use this encoding scheme. So later we'll talk about more advanced encoding schemes. But for now, that'll be it. And so we put a little check mark by it. We solved the XOR problem with TensorFlow-Quantum.